Welcome to the next video lecture on strength of materials.
We will discuss about strength and stiffness of solid and hollow shafts. We will try to compare these under three headings. First heading, we call it as A. I will write a question and we'll try to answer that question. Prove that hollow shaft is stronger and stiffer than the solid shaft of the same material, length, and weight. This is the question. First of all, when the material is same for both solid and hollow shaft, the density of both hollow and solid shaft should be equal. So I'll write rho S is equal to rho H. Here rho stands for density, which is a material property. So when the materials are same, these two has to be same. And when the materials are same, the allowable or maximum stress that they can undergo, that is also same. So tau H is equal to tau H. And when the material is same, rigidity modulus also should be same. GH is equal to GS. And he also says it is of the same length. So LH is equal to LS. And same weight. Same weight means WH is equal to WS. This is weight. That is also same. So this much is given to you. First, let us consider weight of solid shaft is equal to weight of hollow shaft. But what is weight? But weight is equal to volume into density into G. That is weight. So let us substitute that here. Weight of solid shaft. See, solid shaft will be like this. I'll call the diameter as capital D here. Okay, this is solid shaft. And hollow shaft of the same length, it should be of the same length, but it will be hollow. I'll show it like this. This is hollow shaft. So here, outer diameter, I'll call it as DO, and inner diameter is DI. Weight of the solid shaft is volume of the solid shaft into density into gravity. So volume of the solid shaft becomes pi into d square by 4 into L. This is volume of the cylinder into density. Density is rho. So I'll call it as rho H and this as LH into gravity. Gravity is simply G. And on the right hand side, volume of the hollow shaft. Volume of the hollow shaft becomes dO square minus di square divided by 4. This is solid shaft. So pi d square by 4 into LS. LS stands for solid shaft. And into rho S. Rho S means density of solid shaft. Into G is equal to pi by 4 d naught square minus di square divided by 4 into LH means length of hollow shaft into the gravity G. Now here you know that LS is equal to LH, so we can cancel. G can be cancelled. Rho S is equal to rho G. I did not mention the rho G here. I'll write into rho H. So rho H, rho S can be cancelled, and pi by 4 can be cancelled. So you will be left with only d square is equal to d naught square minus di square. And if I take d naught square outside here, comes 1 minus di square divided by d naught square. And let us call this as d naught square into 1 minus k square, where k is equal to di by d naught. Or I can say d is equal to d naught root 1 minus k square. So we got a relation for the diameters of these two shafts in terms of diameter ratio of the hollow shaft. Let us call this equation as 1. We will be using this equation later. Next, let us consider the strength now. Strength of hollow shaft divided by strength of solid shaft. Now the ratio of strength of hollow shaft to strength of solid shaft I am considering. If I can prove that this ratio is greater than 1, it also means that strength of hollow shaft is greater than the solid shaft. But what is this torsional strength? Torsional strength is T by tau, which is nothing but ZP. That means it is actually equal to ZP of hollow shaft divided by ZP of solid shaft. Z is nothing but the polar section modulus, which is the ratio of polar moment of inertia to the radius, right? So I will write it as J by R of hollow shaft divided by J by R of solid shaft. What is J for the hollow shaft? It is pi by 32 into d naught power 4 minus di power 4. This is J. J divided by R. R for the hollow shaft is d naught by 2. This divided by J of the solid shaft, pi by 32 into d power 4 divided by R of the solid shaft is d by 2. So here pi by 32 can be cancelled straight away. 1 by 2, 1 by 2 also can be cancelled. So remaining, if I write, comes d naught power 4 minus di power 4. I'll take d naught power 4 outside here. So it becomes 1 minus di power 4 divided by d naught power 4 divided by d naught divided by d power 4 by d, which is d cube. D cube. 1 d naught can be cancelled here, so it is d naught cube into 1 minus. I will introduce this constant k now. K power 4 I'll write because k is di by d naught divided by d cube. I will split it into d square into d because I want to use equation 1 here. And I'll substitute equation 1 now. So it becomes numerator will be d naught cube into 1 minus k power 4 as it is. Denominator, in place of d square, I will substitute d naught square into 1 minus k square. D naught square into 1 minus k square into d. D is what? D naught root 1 minus k square. Now you see here d naught 2 can be cancelled with this and remaining will be 1 plus k square into 1 minus k square. I'm just writing 1 minus k power 4 in the form of a plus b and a minus b. And denominator is 1 minus k square root 1 minus k square. And you see 1 minus k square can be cancelled here and remaining is 1 plus k square divided by root of 1 minus k square. Now observe this equation, this ratio. See, normally this k is what? It is a ratio of inner diameter to outer diameter, which will always be less than 1. So for any value of k, this ratio will be greater than 1. Right? You substitute any value here, maybe 0.5. 1 plus 0.5 square. Numerator becomes more than 1 and denominator will be less than 1. So obviously it has to be more than 1. What is this actually? It is nothing but ratio of strength of hollow shaft to strength of solid shaft, which is greater than 1 means strength of hollow shaft is greater than the solid shaft. So the conclusion is therefore strength of hollow shaft is more than that of solid shaft. We have proved one part of this question. Hollow shaft is stronger than the solid shaft. Now we have to prove that hollow shaft is stiffer than the solid shaft, for which we need the definition of torsional stiffness. We know that torsional stiffness is defined as ts is equal to T by theta. Torque per unit angle of twist is called torsional stiffness, which is actually Gj by L. This also we know already. Now let us consider the ratio. Consider stiffness of hollow shaft divided by stiffness of solid shaft. We'll consider this ratio. This ratio is what? Gj by L of hollow shaft divided by Gj by L of solid shaft. Here we have considered the same material, so G can be cancelled. Length of hollow and solid shaft is also same. So it is simply the ratio of J. So J of hollow shaft I have to write in the numerator, which is pi by 32 into d naught power 4 minus di power 4 divided by J of solid shaft. Again, pi by 32 can be cancelled and d naught power 4 can be taken outside. Becomes 1 minus k power 4 in the bracket divided by d power 4. D power 4 I'll write it as d square into d square. It's easy to substitute equation 1. The equation 1 is here. D is equal to d naught into square root 1 minus k square. That is equation 1. That I will have to substitute here now. I will substitute. Numerator I will write it as d naught over 4 into 1 minus k power 4. For denominator I will write d square. D square is what? D naught square into 1 minus k square into d naught square into 1 minus k square. Now I can cancel this d naught power 4, d naught square, d naught square. This can be cancelled. And numerator is a square minus b square format. I can expand it. And one of the term 1 minus k square will be cancelled. It will be 1 plus k square into 1 minus k square Denominator is 1 minus k square, 1 minus k square. So this term can be cancelled, and remaining is 1 plus k square divided by 1 minus k square. Again, for any value of k, this will always be greater than 1. So that means stiffness of hollow shaft is more than that of solid shaft. Okay, that's the proof. So this is one of the question that can be asked. Prove that hollow shaft is stronger and stiffer than the solid shaft. You have to do this much. This is question A. The same can be asked in a different way. I will write that here. Prove that weight of hollow shaft is less than the solid shaft of same torsional strength, material length being same. This is just a reverse of what we did in the previous case. Now we have to equate the torsional strengths of two materials and prove that weight of hollow shaft is less than the solid shaft. So what is given here? Material is same, so rho h is equal to rho s. Length is also same, and torsional strength of hollow shaft is equal to torsional strength of solid shaft. This is given. Now we will use this. Torsional strength of hollow shaft is equal to torsional strength of solid shaft. What is torsional strength? Ts is actually T by tau, and T by tau is nothing but Zp. So this is actually Zp of hollow shaft is equal to Zp of solid shaft. Z is nothing but J by R. It's a polar section modulus. So I will write J by R of hollow shaft is equal to J by R of solid shaft. J for the hollow shaft is pi by 32 into d naught power 4 minus di power 4 divided by R. R is d naught by 2 is equal to J of solid shaft is pi by 32 d power 4 divided by d by 2. So this, if you cancel the common terms here, you'll be left with d naught power 4 minus di power 4 divided by d naught on the left side. Right side it will be d power 4 by d, and you can write it as d naught cube into 1 minus k power 4. I'm substituting the ratio of di by d naught as k, and I'm cancelling one of the d naught, so it becomes d naught cube. Right hand side becomes d cube. I can write this as d is equal to d naught into 1 minus k power 4 under cube root. So we got a relationship between diameters of two shafts. Okay, d is equal to d naught into 1 minus k power 4 under cube root. Now we consider the ratio of weight of hollow shaft, weight of solid shaft. This ratio I am considering. Weight is again volume into density into gravity. So I'll write, since density is same for both, I don't have to consider that. I have to consider only the volume here. So it becomes pi by 4 into d naught square minus di square into length of hollow shaft into density of hollow shaft into g divided by pi by 4 d square into L of solid shaft into rho of solid shaft into g. So you can cancel many terms here. LH, LH, rho H, rho S, G, pi by 4. So it becomes d naught square into 1 minus k square. I'm taking d naught square outside. Becomes 1 minus k square inside. Divided by d square. We'll write it like this. D naught square into 1 minus k square. The denominator d square, if I write, becomes d naught square into 1 minus k power 4 to the power 1 by 3 is there, but into 2 will also be there, so it becomes 2 by 3. So d naught square again can be cancelled, and it becomes 1 minus k square divided by 1 minus k power 4 whole power 2 by 3. This last term now, the ratio, which for any value of k, you substitute any value of k less than 1 now, the ratio will be always less than 1. If you want to check it, you start substituting from 0.1 to 0.9, any value. This ratio will always be less than 1. So for given material length and torsional strength, weight of hollow shaft is less than that of solid shaft. Now here we have considered two shafts of equal torsional strength. We can also consider equal torsional stiffness. That is another heading. I will do that here. Question C. Compare the weights of solid and hollow shafts based on torsional stiffness. Based on torsional stiffness means torsional stiffness is equal. We'll write it like this. Hollow shafts when torsional stiffness of both are same. We know that torsional stiffness T by theta and T by theta is equal to Gj by L. So here he has given torsional stiffness of hollow shaft is equal to torsional stiffness of solid shaft. So Gj by L I have to substitute. So Gj by L of hollow shaft is equal to Gj by L of solid shaft. So you cancel G because material is same. Cancel L also because length is also same. This is nothing but pi by 32 d naught power 4 minus di power 4. This is J of hollow shaft, which will be equal to pi by 32 into d power 4. I can take d naught power 4 outside here. D naught power 4, 1 minus k power 4 is equal to d power 4, or I can write d is equal to d naught into 1 minus k power 4, the fourth root. This is equation 1 now. We have a relationship between the diameters of solid and hollow shaft based on the equal torsional
Stiffness.
Now let us consider the ratio of weights. So consider weight of hollow shaft and weight of solid shaft. So this ratio, when you consider, you know that weight of shaft is nothing but the volume. Volume of hollow shaft is pi by 4 into d naught square minus di square into length of hollow shaft into density of hollow shaft into g divided by for solid shaft pi by 4 d square into ls into os into g. So you can cancel these terms. So remaining terms will be d naught square into 1 minus k square divided by d square. D square I can substitute from equation 1 now. So it becomes d naught square into 1 minus k power 4 to the power 2 by 4. So it becomes 1 by 2. And d naught square again can be cancelled. It becomes 1 minus k square divided by root of 1 minus k power 4. Now observe this ratio. For all the values of k, this will be less than 1. Will always be less than 1. So for same material, length and equal stiffness, weight of hollow shaft is less than that of solid shaft. Now based on this, we will try to solve a problem now. Problem is here. Compare the weight of solid shaft with that of hollow one, having the same length to transmit a given power at a given speed if the material used for both the shaft is same. The inside diameter of the hollow shaft is 0.6 times the outer diameter. We have to compare the weights, means how much weight is saved by the use of hollow shaft. Here K is given, di by do is given as 0.6. Having the same length, LH is equal to LS. It is for transmitting the same power. When the power is same, torque also should be same, because power is torque into angular velocity. So power, when it is same, torque also should be same. And since it is made up of same material, tau also should be same, and G, rigidity modulus, also should be same. Now with this, first we will try to compare the torsional strength, because there are two things. You can consider torsional rigidity also. If torsional strengths are equal, this is KCA. There are two cases now. Then torsional strength T by tau should be is equal to T by tau. This is for hollow shaft, this is for solid shaft. They should be equal. T by tau is nothing but ZP. So we have to write the ZP for both and equate. ZP is nothing but J by R. So J for solid shaft is pi d power 4 divided by 32 divided by R. R is d by 2. It should be equal to pi by 32 into d naught power 4 minus di power 4 divided by d naught by 2. If you cancel this pi by 32 and 1 by 12, all that, you will get d power 3, because d power 4 by d is there. So d cube it becomes. is equal to, on the right hand side, if I take d naught power 4 outside, becomes 1 minus k power 4 divided by d naught, or it is d naught cube into 1 minus k power 4. Now you substitute k here, d naught cube into 1 minus 0.6 power 4. So this gives you the relationship between the diameter of the solid shaft and outer diameter of the hollow shaft. So this will be 1 minus 0.6 power 4. If you calculate, comes out to be 0.9548 d naught. Now we'll consider the weight, compare the weights. So consider, I will write it as weight of hollow shaft divided by weight of solid shaft. You know that weight is volume into density into gravity, and density and gravity are same for both. So volume will come into picture. In volume also, area into length. Length is same. So only area will come into picture here. So area of hollow shaft is pi by 4 into d naught square minus di square divided by area of solid shaft is pi by 4 into d square. And here, if I take d naught square outside, comes 1 minus k square divided by d square. D square I substitute from this equation 1. So d square becomes 0.9548 square into d naught square. K here also I will substitute 0.6. I'll substitute it as 0.6. So here d naught square will cancel, and the remaining ratio, if you calculate, comes out to be 0.702. Therefore, weight of hollow shaft is 70.2% of the solid shaft. That's the conclusion you can make. This is case A when we equate torsional strength. Same can be done for case B with torsional stiffness also. We'll do that here. Case B. Torsional stiffness or torsional rigidity is what? It is T by theta. T by theta of hollow shaft is equal to T by theta of solid shaft. But T by theta is nothing but Gj by L. We know that. So this, if I substitute Gj by L of hollow shaft is equal to Gj by L of solid shaft, I can cancel G here because it's made up of same material, and length also I can cancel. It is simply the equation of polar moment of inertia J. For hollow shaft is pi by 32 into d naught power 4 minus di power 4. For solid shaft it is pi by 32 into d power 4. Again, if you take d naught power 4 outside, becomes d naught power 4 into 1 minus k power 4 is equal to d power 4. You substitute k is equal to zero point 0.6 now. So this will give you d equal to 1 minus 0.6 power 4. I'll write d power 4 only into d naught power 4. If I simplify this, I will get a d value of 0.966 d naught. So now let us compare the weights. Consider weight of hollow shaft to weight of solid shaft. Again, when we compare the weight, only cross-section area will come into picture. So pi by 4 d naught square minus di square divided by pi by 4 d square. If I take d naught square outside, 1 minus a square divided by d square is nothing but 0.966 square into d naught square. And here in the numerator, this is 0.6 square. 0.6 square. So when you substitute this and simplify, you will get a ratio of 0.686. Therefore, weight of hollow shaft is 68.6% of that of solid shaft. So like this, you can compare the weights of two shafts. Now I will give you a problem for homework. It is a solid shaft which has to transmit a power of 1000 kilowatt at 120 rpm. Find the diameter of the shaft if the shear stress of the material must not exceed 80 Newton per mm square. Maximum torque is 1.25 times the mean torque. What percentage of saving in material would be achieved if the shaft is replaced by a hollow one whose internal diameter is 0.6 times the external diameter? Length, material, maximum shear stress are the same for both hollow and solid shafts. So this you try to solve and you should get these answers. I have given the answers also.